Good afternoon, everyone, and welcome to the second seminar of the Brussels Institute for Advanced Studies. So it's my pleasure today to introduce the first speaker. So we will have two speakers today, and the first speaker is Professor Yilin from the Department of Automation of Tsinghua University. So he has a very impressive CV and will introduce us the world of MPC. And so we are so curious, and the floor is yours.
Okay.
Thank you.
Thank you, Luca, and also thank you, Anya and Emanuele for inviting me here. And I'm sorry for my English because I haven't given an English seminar for a very long time. So if I have any problem with, please stop me. So my main background is on control, and after I go back to Tsinghua, I did a little bit on robotics. So today I want to introduce you a little bit of things we do on combining control and robotics. So one thing we really want to do in our lab is we want to let robots do some very agile and aggressive maneuvers. So all the things I show here are actually done by human drivers. So you can see this one is a human driver that is doing an evasive maneuver on a very high-speed car. And this one is actually this one is more interesting because it's a remote control car. So the human are not really sit in the car. It's just doing control using the visual loop, which we know is very slow for a human. So, but we can see that a human can control all these kind of systems pretty well. And we are actually interested in how, to achieve this on autonomous robot, because back in China, we have some collaboration with some of the autonomous driving companies, and they are interested in how to safely control the robot on autonomous car on a slippery surface. For example, if you have heavy snow or you have an icy surface, you want the car to be controllable, not hit the other people stuff. So if you look at the traditional control approach, if you want to have such a very agile system, the default thing we want to do is so-called Model Predictive Control. So here, this is done by Professor Ralph D'Andrea from ETH. This is probably 10 years ago. Probably you cannot see very clearly, but he is basically throw a ping pong ball, and the quadrators are supposed to hit the ball and return the ball back to his hand. So not only does the quadrator need to intercept the ball at a certain point, but he also needs to do it at a certain angle and velocity. So, and also this one probably you are more familiar with. This is Alice from Boston Dynamics doing all these very human-like maneuvers. So I think a lot of you probably are not that familiar with model predictive control, so I can skip a few slides and give you some intuitions behind these sort of controllers. So typically in a control task, we need to deal with two things. One is we want to sort of minimize some cost. The cost is basically we want so this x is the state of the system. For example, you can consider the speed of the car and its heading, its position as the state. And we wanted to track certain reference signal. So this is R is certain reference signal, and we want this to be the state of the system to be as close as to the reference as possible. And at the same time, we have some penalty, some regularization terms, if you are familiar with the AI language here. So here is so this U is a control input we give to the system, like how much brake, how much steering we put into the system, and we don't want a very aggressive control. So this we also put some penalty on how large your control will be. So this will be our cost, and at the same time we have some sort of safety constraint, meaning that the car needs to stay in this region, and for example the maximum steering is this much, the maximum acceleration or deceleration is this much. So all of this can be captured by some sort of constraint here. And of course, if you just doing a very simple control, you can say, okay, I just find one control which is what we call U0. So here this K is for the time index. So I can just find a single control that try to minimize this objective and try to stay in this safety constraint. But usually that's not enough, because for a lot of control tasks, you need to plan ahead. Instead of looking at satisfying the constraint at the current step, you need to look a few steps ahead. So that's where this is called the model predictive control, because you need to have a predictive model. So instead of saying just solve for the control at time 0, you also need to have the control for time 1, 2, 3, 4. Up to a certain time horizon. You want to say, okay, if I apply this long sequence of control input, I will always stay in this safe region and I will satisfy these constraints. So these are the basic idea for MPC if you are not really familiar with this. Of course, if you look at this formation, you will see there are a few key challenges. One thing is because you need to look ahead. You don't only look at what happened at the current step, you need to predict. Then how accurate is your predictive model is a very big problem. If your predictive model is bad, then your planning will be bad, and this control may even make the system to be unstable. Another problem is how do you implement this controller, because you are really trying to solve an optimization problem online, and usually you need to solve it at a very high speed, like 50 Hertz. So whether you can really solve a very complicated problem online in real time, that's also very challenging. So nowadays, people are trying to move to this reinforcement learning based controller. So usually people use this so-called deep reinforcement learning to learn a neural network that is trying to control these kind of robotic systems. For example, this is done by OpenAI, I think in 2019. This is a robotic hand that is trying to manipulate a Rubik cube. And this is, actually there are a lot of people doing this. I'm just picking one video. This is from CMU, that is a robot dog trying to traverse through some uneven and slippery terrains. So for all these problems, it's actually quite challenging to do using the traditional MPC-based approach, because you don't have a very good model. You don't have a predictive model that can tell you what will happen next. So this is remarkably successful for using reinforcement learning to solve all these kind of problems. And we actually did something in our lab. So this is what we did for controlling a car in a drifting maneuver. So here you can see we can do a 8-figure shape, and we can also do it consecutively like this. Yes. There are some other robotic projects we go through in our lab. So because I think that might be interesting than a lot of formulas, so I will show it here. So this is a project we did with a Chinese company. They are trying to do this autonomous driving semi-trucks that is shipping coal from one city in the inner Mongolia to a harbor that is about 800 kilometers. So currently they can only do autonomous driving on the highway, because that's kind of simpler, because you only need to go straight. So if you want to control this kind of system in a very sort of narrow spaces like in the harbor, you need to do a lot of planning and control to do this. And it's actually extremely challenging to drive these semi-trucks backward, because the system, if you go forward, is actually stable, but if you drive it backward, it can become unstable. So this is what we are currently developing for them. We also did something of robotic hand. So this is done by teleoperation. So there is some other guy that is having a glove and also wearing a VR glasses. So he will see what this robotic hand see, and the system will map the motion of his hand to the robot hand here. So we have also did some project here for this kind of manipulation task. Yeah. So, yeah, like I said, I think there are some, we have done a lot of things using reinforcement learning, and there are also a lot of other very success stories using reinforcement learning to do this robotic task. And I think people are now trying to consider like why do we need reinforcement learning, and I think this is a very good observation from, this is from a paper of from University of Zurich. So they published it on Nature in I think in 2023. The title of the paper is Champion Level Drone Racing. So they develop a reinforcement learning algorithm that make an autonomous drone actually races faster than human pilot. So what they observe is that the fundamental advantage of reinforcement learning over, for example, optimal control is not that it can optimize better, because optimal control, as we know it, is optimal. So regardless of what problem you send it, it should give you the optimal solution. But the thing is, in reinforcement learning, as we find out later, that you can put a lot more objective into the learning framework. So a lot of times it will be able to optimize a better objective. So that's what we observe. But if you look at this sentence, I think one thing that is missing is why should we do reinforcement learning to learn a neural network? Because this sentence has nothing to do with the things to be learned. It's only the learning algorithm, not the things to be learned. So I think we have to make a distinction here. So we want to ask ourselves, is a general neural network really necessary? Of course, general neural networks, as we know, have universal approximation properties. But do we really need something that can express every possible control law? And also another thing is, although in the literature, all these so-called deep reinforcement learning, they use neural networks, they are actually not deep at all. So if you look at all these robotic neural network controller for robotics, they are usually just 3 layers. So it's a very shallow network that people probably could train back in the 1990s. So it's a very shallow network. It's not really deep at all. So that brings a lot of question on whether we should really use a neural network, because it's not like a huge like transformer that is doing all these control tasks. So if we go back to the control literature, we can see that people are using different terms other than learning to learn different kind of controllers. For example, if you have a control background, you know one very famous controller is called the PID controller. It probably solves 95% of all control problems. So it will have 3 parameters that can be learned, or actually you can also call it self-tuning. So this was developed by Professor Carl Ostrom back in 1970s. And also you can have some what we call a linear feedback controller that is saying that my control is just a linear function. So this K is what we call control gain, linear function of my current state. And there are a lot of ways to learn this kind of controller as well. And of course, there are people working on learning this so-called model predictive controller. You can think like all of these things potentially you can try to learn, like the cost function, the predictive model, the constraint, the terminal constraint. All of this you can try to learn. Yeah, so what we see here is actually there will be a spectrum of things that you can do tuning or learning or whatever you call it. right? So on one hand, on one side, you have this very simple controller. You have PID. You have this linear controller that is very easy to understand, even if you don't really understand the learning algorithm. As long as they give you a linear controller, it's very easy for you to verify that this controller is stable or not. On the other hand, you have this so-called neural network-based controller that nobody really knows what it is doing. There is a little bit of work on how to verify this, but the complexity actually are really high. So in reality, you cannot do anything about it. And there will be something in the middle, because we know all these simple linear controllers, there are some performance limitations. So they cannot there are some limitations because the control law are very simple, so they are not expressive enough. So our goal is to say whether we can find the correct balance, right? This is more, I think, more like a very old-fashioned machine learning, where you want something to have the correct structure, the correct complexity, so that it's expressive enough, but it's not too expressive, that it's very difficult to verify. So that will be the focus of our talk. So now I have to go through some mathematics. So in fact, the title of the talk is a controller inspired by MPC. So if we go back to this MPC formulation, and if you are not really in the control background, you can just think of it as a huge optimization problem. So here, really, the thing you want to optimize is the future control input. You want to know what kind of control I need to add in the next n steps in order to make the system satisfy the constraint and at the same time try to minimize the cost. If you look at this quadratic programming problem, you will see that actually this x is somehow redundant, because all the x are actually determined by u. So once you know the control input, you can use this linear equation to determine all the future state. That's the idea. So you can basically say, okay, I will just remove all the redundant redundant optimization variables, and I will arrive at some problem like this. So the objective function will be a quadratic function of the control input, because x is actually linear with respect to u. So if you replace all these x by u, you will get a quadratic function like this. And all the constraints are linear constraints. So you will get a polytope constraint on u like this. And here you see in this problem, if you look deeply, you will find out these matrices P and H. They only depend on system parameters. So if you know the predictive model, you already know all these P and H matrices. On the other hand, these vectors for the quadratic programming problem, they will linearly depending on the current state. So this is the state at the current time and the reference you want to track. Okay, so this will be the quadratic programming problem. And now we can just basically throw caution into the wind and say, okay, well, we know all these like quadratic, the structure, the linear structure, the QP structure. We will just say, okay, all the matrices, instead of deriving it through the system model, we will just say it's a learnable matrix. Okay, so now I just change everything to be learnable. So everything with a tutor on top of it will be a learnable parameter that I needed to tune. And of course, if my problem have the correct number, correct size, meaning the correct number of optimization variables and constraints, I can represent my MPC in this form, right? So in some sense, this one should do at least as good as model predictive control. Okay, so this is our goal, is to learn something like this. And if you want to do that, what you really need to do, if you look at all the learning framework, what you really need to do is you need to calculate this. You need to basically make the controller so-called differentiable, meaning that you need to be able to calculate the derivative of my optimal u with respect to a little bit change in my parameters. So if I change all these P, W, B matrix by a little bit, how much my control U will change. So that's the thing you need to calculate. Once you've done that, basically everything will work. You do like a backward propagation and do calculate the policy gradient, and yeah, everything will work as long as you can compute this. And if you are familiar with optimization, this is called sensitivity analysis. This means how much the optimal solution of an optimization problem will change if my parameter in that optimization problem change a little bit. And classically, if you want to do sensitivity analysis, this is usually done through KKT conditions. But some people go through that route, but it's very difficult because, for one, if you want to find a KKT solution, it's usually very time-consuming. The other is sometimes you are learnable. You learn a problem that is infeasible, and at that time, this KKT condition, you cannot solve the KKT condition because the problem becomes infeasible. So usually, in our experience, it's like the problem will be just in between feasible and infeasible. It will just be on the boundary. So a lot of time, if you try to solve this for KKT, you will run into disasters. So what we do here is what we call unrolling. So instead of going through the KKT, so we look inside on how do you solve this QP problem. And usually, if you are familiar with the optimization literature, there are a few ways to solve the QP problem. You can do the Newton's method, that's the second order method. So, for example, the famous interior point method will fall into this category. And for QP, you can also do so-called active set method, meaning that you find which constraint are active and which constraints are not. But all these are a little bit more complicated, so we will be looking at the so-called first order method. So let me introduce you with a very simple method called the projected gradient descent. So for example, if you look at a QP problem like this, first, if you don't look at the constraint, so if you just want to do a unconstrained problem, so you will just look at this quadratic cost function. You will draw the contour lines of this objective function, and what you can do is you can just do a gradient descent. So you will start here, and you say, okay, this is the direction of my gradient, and I will go to the opposite direction of my gradient, and I continue to do this. I will eventually reach this point, which is -1, That is the optimal point. So, and of course, if you look closely, the gradient descent step, because this is a quadratic function, your gradient will just be a linear function. So the gradient descent step is really just a linear transformation of this x vector, okay? But now we have some constraint, right? We want both of these x to be positive, so the x needs to stay in this green region, which is a feasible region. So instead of just doing pure gradient step, you will add one step called the projection. So you start here, you do one gradient step, you find out that you actually exit the feasible region. At that time, you will do a projection. You say, okay, I will find a point in this feasible region that is the closest to this point after the gradient step. So you will alternating between gradient descent and projection, gradient descent and projection, and then you will converge. This is something you can prove. So, and if you look at the projection, this is actually also quite simple because you are looking at projecting a point into this positive region, so you can just look at each dimensions individually. So you can look at x1, say if x1 is negative, I will make it 0. If x1 is positive, I will not do anything. So the projection will be just something like this. Okay, so now we can look at this in the picture, something like this. So you start with certain point. So this point we call it, you can actually choose whichever point you start. But here we just start at the origin. We start at 0. We will alternating between gradient descent and projection, gradient descent and projection, and eventually we will converge to the correct optimal solution of that problem. And we can find out that all these learnable parameters will somehow enter this, basically enter this gradient descent part in certain ways. That's eventually the case. Okay, so that's all the explanation if you are from an optimization background. But if you are from the machine learning background and you look very closely to these operations, you will find out, okay, this is what we call an affine layer in the neural network, because you are just doing a linear transformation of the x. And this is just the famous ReLU unit, right? Because you are projecting it to positive. So, of course, in optimization, you can call it gradient descent and projection. But in neural networks, you will just call it a affine layer and ReLU. And you will just continue to do this until you converge. So this is nothing but a very, very classical recurrent neural network, right? It is recurrent because all the affine layers are essentially the same. So we are doing the same gradient descent step. So, so we will have something like this. Of course, this is one algorithm to solve the QP, that is projected gradient descent. But if you look at all the other algorithms like ADMM, PDHG, eventually you will most likely arrive at something like this. It's just the affine layer, the ReLU layer are slightly different. So at that time, we get two things that are representing the same controller, right? On one hand, we say, okay, our controller is actually an optimization problem. It's an optimization problem of this form. On the other hand, we say, okay, our controller is actually a recurrent neural network. It also has some structures built inside, because all these parameters you need to put in a certain way. There are some parts that are 0, some parts are positive semi-definite, so you need to have some structure there. But these two things are more or less essentially the same thing. If, for example, if you iterate for long enough such that it converges, it will essentially give you the same thing. But because we have two representations, we can leverage the benefit from both, right? So on one hand, we can say, okay, this neural network, we can just throw it into PyTorch and all these reinforcement learning frameworks, and it will just work. You don't really need to write any more code to be able to learn all these parameters, because all the backward propagation are already done by PyTorch and other learning frameworks. On the other hand, once you have this, you can recover this QP representation. You can go back to the optimization problem saying, now I have a very compact representation of my controller. Probably I can do certain things. For example, in MPC, what we care about is the verification of the controller. So that goes back to the title of this talk. So if I have a very compact QP representation, what we can do is we can try to do certain verification. But because this is very control theoretic, so I will just give you a very brief idea. So for one thing, if we want to verify the controller, we need to basically, there are two things we need to prove. One is the controller will be so-called asymptotically stable. That means if you start at a certain point, you will always go back to 0. So that's called asymptotic stable. But because the controller is based on an optimization problem, an additional thing you need to verify is whether that optimization problem always have a solution. If at a certain point this optimization problem is infeasible, then you run into trouble, right? So you will also need an additional thing called recursive feasibility, meaning that if that optimization problem have a solution now, it will also have a solution at the next step. So then you can use induction to say, okay, this one will always be stable, something like this. So if you look at the recursive feasibility, you run into something like this. Basically, we want to say if, for example, if the optimization problem starts within this polytope, it will always remain in this polytope. And this polytope will satisfy all the safety constraints. That's one way to prove that the optimization problem will always be feasible. So you will end up with some problem like this. This will be a non-convex so-called QCQP problem, meaning quadratic constraint, quadratic programming problem. And if you can solve this problem and you find the solution is non-positive, then you prove that this set will be so-called forward invariance. So you will always stay in this set and you will always have a feasibility. So I will not really go into details, but you can see that here we say that this quadratic programming representation of the control is actually quite important because we need something like this in order to convert all the proof into a big non-convex optimization problem. And also, similarly, you can prove stability in this manner. So you create another optimization problem based on the controller you learned, and then you can do this. So this is an example we try. This is from a very famous MPC book. So for this, this is a so-called double integrator. I can give you a simple explanation. You can consider this as a car. So the car is just a one dimension. So we are just consider the car on a one-dimensional space. So there is no steering. So the car will have a position and a velocity, right? And you can control the acceleration or deceleration. You are controlling the brakes or throttle. So something like this. And this U will be the brake you apply to the car. And this X will be the position and also the velocity. So you have some constraint saying that the velocity and the position of the car needs to be constrained between +5 and -5. Meaning, so you can visualize it as something like the car is on this table, and if you go too far, the car will fall off the table. Okay, and you have some limit on how much brake you can apply. So this so you can only apply this amount of acceleration and deceleration. And also here, that's very interesting in the cost is that the braking is very expensive. So you have a huge penalize on how much on the brake you apply. So if that is the case, I need to probably introduce you with the concept of like, for example, for the car, the safety region is not really this region. Meaning that if, for example, if I'm here, although I haven't fell off the table, but maybe I'm going too fast and I cannot apply an infinitely large brake. So even if I haven't fell off the table, I will inevitably fall off the table in the future. So I pass some point of no return, right? So this is the concept. Like the safety region is not really this whole table. It's a much smaller region. So in fact, if we try to draw the safety region, you will find out this will be the purple region will be your safety region. Meaning that if you are inside, there will be some braking strategy that can keep you on top of the table. But if you are outside this region, you are doomed. There is no way for you to stay on this table. You will eventually fall off, even though you haven't fell off right now. So, but if you look at so this green line is the MPC controller. So if you look at the MPC controller, basically, like I said before, it's looking a few steps ahead, right? But what may happen is if you don't look far enough ahead, you will say, okay, I won't fall off in the next 3 seconds. So because the braking is so expensive, I will not really hit a lot of brake. But maybe if you don't hit the brake now, you will fall off on the 4th second, right? So if you have a very short looking ahead horizon, then for the MPC, you will be doing something like this, even though here you have some strategy to stop the car, but because you don't look far ahead, you don't realize there is danger ahead, you will not hit the brake fast enough, so that eventually you will fall off the cliff. So that's what happened for the MPC. And you can prove that for the MPC, actually, the stable region is this deep blue region. So only if you start inside this smaller region will you be able to stop the car. But for us, because we are training this controller in the using reinforcement learning, and in reinforcement learning, we can set a time period to be like 300 steps or a very, very long time. So we are actually be able to overcome this short-sightedness here. So for example, if you look at here, we will be able to, even MPC fails, we will be able to drive the car back to the origin. And we can actually prove that using the framework I told you before, that this very large light blue region will be the region of stability, meaning that wherever you start at this light blue region, you will be able to drive the state safely back to 0. So this is almost the same as the maximum maximum pink region, right? So this is very nice. And also, if you look at here, although MPC right now it can stabilize the car won't fall off, but because it's so reluctant to hit the brake, it's actually making this thing very bad, right? You have a lot of oscillation here. So you can see that the MPC, there is a huge cost. Although at the first few steps, the cost is low, but because you don't hit the brake fast enough, eventually you will incur a lot more cost. But for us, you will have a much smaller cost. So that's one thing with this kind of controller. Okay, I think because all of you are expert in reinforcement learning, and I won't go really deep, but here all I want to say is, this is a very typical reinforcement learning setup, and a lot of times for real-world control, because you don't really have a very accurate model of the system. So instead of simulating one system, what you really want to do is you do the machine learning people say domain randomization. So instead of say the system will evolve according to this nominal system, you say, okay, probably the system parameter will vary a little bit in this space. I will also add some noise to the whole process, and I want the controller to be able to control this kind of uncertain and stochastic systems. So I need to add this domain randomization here. And also another ingredient you want is you want to use the GPU to do all this simulation. But it's not really a very huge problem. So you can just write a very simple PyTorch code, which we have a repository that is doing this. Yeah. So you can just do reinforcement learning. Okay, so now let's look at some examples. So this is a very famous control example developed by Professor Carl Johansen from KTH. So this is a 4-tank system. So here the state of the system is basically the water level of these 4 tanks. And there are 2 pumps. So one pump is pumping water to tank 1 and 4, and the other is pumping water to tank 2 and 3. And the water will drop off the tank like this. So we want to control the water level of the tank to be in between some minimum water level and maximum water level. So this one is a little bit challenging because there are water that are falling down here. So, for example, even if your water level here is okay, maybe in the future, because there are so many water here, this one will be filled, and this one will go above the maximum water level. So this will be some of the results. So if we look at this is a classical MPC approach here. This 2 and 16 means look ahead horizon. So 2 meaning that I look two steps ahead, and 16 means 16 steps ahead. You can see that if I have a very short look ahead horizon, then the MPC is not doing so great, because like we said before, because of its short-sightedness, it may fail the constraint. Right? This can be improved by looking further ahead or adding something what we call a terminal set constraint. On the other hand, if you look at all these learned algorithms, so this is, we use RL to learn a neural network. So these are the QP controller that we learned in our proposed QP controller. So here we have some parameters here. So this 4 basically means the same size problem of MPC as a 4-step look ahead MPC. So this 16 means this QP problem will be the same as the MPC problem of 16 steps look ahead. And you can see that the fail percentage is very small, because essentially we are looking much further ahead than the MPC. And the cost is similar. So here there are some problems, some caveat, meaning that the cost, if, for example, if the experiment fails, then the cost will be accumulated. The accumulation of the cost will be stopped at the time they fail. So if you fail a lot of experiments, meaning that your cost will definitely be smaller, because you early terminate the whole process. Okay, so you will see that MPC, we have similar performance as MPC in terms of cost. But MPC, because it's solving an optimization problem, and a lot of times the optimizer doesn't really, you don't know how many iterations you need to solve that optimization problem. So you can see that the computation is not fixed. You don't know how much computation you need. But here, we implement this using a neural network with a fixed number of iterations. So the number of computation is actually fixed. So here you can see these numbers, they don't fluctuate. On the other hand, so this problem is actually quite favorable for MPC, because you have the exact model. And if we just add a little bit of uncertainty and stochastic noise into the system, for example, we let a 2% variation in all these parameters, and we add a little bit of noise, you will find out that MPC will fail almost every single time. And on the other hand, there are some ways to make this MPC to be robust to noise, but all of these methods have a huge computation cost, because you need to basically compute online, like saying, instead of say, okay, if I apply this control, I will go like this. I need to say, okay, if I apply this control, I may, because of uncertainty, I may go here, I may go here. I need to consider all the possibilities that my future trajectory will go. So this will make the computation much more challenging. But on the other hand, you see, for all these reinforcement learning-based techniques, because we solve the robustness problem during the training phase, we are training this controller in an uncertain environment, so that when during online deployment, we don't actually have additional cost in terms of computation. And also, we are very robust against all kinds of uncertainties, because we have already seen these sort of uncertainties in the during training. Okay. Okay. So yeah. And also, we did some real-world experiments. This is balancing a so-called inverted. So here we are balancing an inverted pendulum. So the pendulum are supposed to follow a sinusoid signal. So this one is a little bit difficult to due to two reasons. One, there are a lot of unmodeled dynamics. Like for example, here you have this cable. This cable is actually pulling the motors. So there are some force that you don't foresee in the. It's not that easy to come up with a very good model. Also, this one, because the pendulum is rather short, you have to control it at a frequency like I think around 100 hertz. Below that, this one will not be very stable. So if you use MPC, then you need to use some tricks to make the computation to stay in 10 milliseconds, basically. But if you use our controller, everything will go very well. And we also did this one with a car example. So this one can, even for this is a nonlinear system, this kind of controller can also make this car do this drifting motion. Yeah. So okay. So how much time do I have? Okay, so I think I will go briefly into this because in my talk I say data-driven learning. So I haven't touched any like data-driven stuff. So I want to introduce a little bit of this data-driven things. So actually one thing that is quite important is in the reinforcement learning, you want this environment that you simulate on the GPU to be as close as to the real system as possible, right? Otherwise, you are basically learning to control a different system than the real one. So you want to do that, and usually it's quite challenging to do that. Typically, what people do in control is they collect a lot of system data, and then they say, okay, let's run an identification algorithm to come up with a model of the system. And then they will try to design a controller based on this model. But so in some ways, it will be something like this. If you, this is more. so you will need some sort of data to fill in. If you, for example, look at the MPC problem here. The important thing is you will need this A matrix and B matrix that is modeling the evolution of the system dynamic. So, but on the other hand, if we want to do it in a more direct approach, so here, if we want to just collect some data and try to generate a controller instead of trying to identify a parametric model, what we can do is this is for the system that have no noise. This is so-called the Williams lemma. So it's basically saying the following. So because we assume the system is sort of linear, so if we add the system's trajectory together, we will get another valid system trajectory. Meaning that if you, for example, if you put in, like if your control is 1, the system trajectory is like this. Then if control is 2, the system trajectory will be 2 times that's the things you put when u equals to 1. So you can combine the trajectories. You can do a linear combination of the trajectory, and the thing that is output will also be a valid trajectory. But on the other hand, this lemma also tells you that if certain conditions hold, then all the feasible trajectory, all the valid trajectory will be a combination of the trajectories that you store in this library. So the way you use this lemma is here you will collect some input-output data of the system. You collect enough data, and then you will say, okay, all the possible trajectories will be a linear combination of the things I store in my behavior library. So this is called a behavior model of the system. So for example, you can, if you look at MPC, typically we are solving, try to do something like this, but instead of have an explicit system model A and B here, we can also do something like this. So this is basically the path trajectory that we store in a behavior model. So we put all the trajectory here. We are having this G, which is a linear combination of the path trajectories, and we want it to fit the data we observe and also this u and y, this future u and y are the things that we are the optimization variable that we want to design. So you can replace this parametric model by a behavior model like this. So what we did here is we say, okay, if you have, instead of a deterministic system, because here like there is no noise, so everything will, so you can just add everything together, there is no problem. But if you have a little bit of noise, the first thing is your future state or your future observations will not be a deterministic one. Your future observations will actually be a stochastic process. So instead of a fixed one, it will become some, there will be some stochasticity here. And you cannot really just simply combine this and get one trajectory. Instead, you need to do some sort of, either you want to model this distribution or you want to do some sort of sampling from this distribution. So here, what we are doing is a so-called generative model, meaning that we want to sample from this distribution. So instead of here put a fixed coefficient for the linear combination, we have to put in some random coefficient so that you will have some randomness here. So this is a little bit complicated, and I don't think I have enough time. Anyway, so here basically you can put certain randomness inside. So this randomness will be according to certain Gaussian distribution, and you can prove that if you have enough data and somehow you have enough, this is looking back distance, then this generative model will converge to the true distribution at certain rate like this. So this number of samples, you will take the square root of this number of samples because this is somehow related to the central limiting theorem. You usually have something like this, and this depends on the look back distance. And you can create some model of MPC using, instead of using this parametric model, you can use this so-called behavior model we propose, and you can do the same MPC. Okay, so we try to combine all these together. So we get some table like this. So here, if you are still using MPC, but you can either use a true model or you use a data-driven model, data-driven behavior model from us. You can see that more or less they have similar performance. So the fail rate and the cost are the same. Of course, because we have a generative model of the system, we can also put it into our RL framework. We can use it to replace the environment. So here we have some comparison. So if you put the true model as the RL environment, you will have a very good response. But if you put this generative model, because here we only have finitely many samples, so we will have worse performance, but I think it's okay. On the other hand, there are also a lot of people working on this offline reinforcement learning. But in some sense, if you do offline reinforcement learning, you are not really leveraging the fact that for some system you can actually compute the linear combination of the trajectory. That will also be a valid trajectory. You are not really using the factor there. So basically, this one with very limited data, they cannot really learn anything because the cost is so high. So this is basically like a very conservative strategy that don't really control the system, just trying to avoid violating the safety constraint. Okay. So to conclude, I think we talk about a few things, and I think one thing is reinforcement learning. I think is has a huge potential for both control and robotic applications, and the main reason is being that it tries to optimize a better objective. So what we think, for example, in reinforcement learning, you can optimize something that has a huge look-ahead distance. That's one thing that's not there for MPC. Another thing is you can add a lot of uncertainty, a lot of randomness into your system in your simulation to learn a robust controller. That's also very difficult to do in MPC. But I think one thing that is probably questionable is whether we should use reinforcement learning to train a neural network. So I think that for a lot of applications, probably that's overkill for the task we want to do. So, but then there is this problem of what is the thing that need to be learned, what controller we need to learn, what is the correct architecture. We want something to be expressive but not too expressive, so there needs to be some sweet spot. And we think an optimization-based controller could be a good candidate. So basically that's what we propose in the first part of the talk. The other part of the talk, I think because I go really fast, so probably it's not that clear. But we think that another very important thing is how do you use real data collected from the system to build a good model of the system that can either be used in model predictive control or you can be using it in reinforcement learning. So for that, I think what we propose is a so-called behavior model, and that you can go around very complicated system identification. And I think possible it's also okay to generalize this to nonlinear systems. So right now we are saying, okay, for linear system, you can just simply add two trajectory, and it will give you another valid trajectory. But for nonlinear system, we know that you can do some local linearization. So you cannot combine two arbitrary trajectories. But if the two trajectories start to be very close to each other, you should still be able to combine them to generate a valid trajectory. That's basically linearization around certain operating point. And if you are interested, so this is the code for the paper, and these are also the code for the reinforcement learning of the QP controller we create. You will need a GPU to run this, but it will just take you, if you have a GPU like not a very fancy one, you just need like a 3080, something like that, like a few €100, I don't know, a few €100 GPU to run this. It will give you a controller probably in 10 minutes. And if you put all the ABC matrix inside, it will give you an answer. And if you encounter any problem, please let me know. And we are very eager to see whether this can be used in some real applications. And I think that's the end of my talk. And thank you for listening.
Thank you, Yilin, for this very interesting talk. And I think now is time for discussion. So questions from the audience, even the audience online. Alejandro.
Thank you for the presentation. Is it on? Yes? Yeah. Okay. Thank you for the presentation. I have a question because you mentioned that offline reinforcement learning was not well, that there were limitations at least. Can you explain a bit? Because, I mean, as far as I understand, the system does not change over time. I mean, so why is it?
I think the main problem is regarding the sample complexity of offline reinforcement learning. So usually, because in offline, I'm not really an expert, but my explanation is something like this. So since they are dealing with arbitrary system, here we are only dealing with a linear system, basically. So if you are dealing with arbitrary system, you cannot really add trajectory together. You can only say, okay, for the trajectory, you can only do something like this. You cannot do linear combination of the trajectory. So once I have a trajectory library, the number of valid trajectory or the number of trajectory that I can generate from this library is very limited in offline reinforcement learning. Of course, if you have like an infinite number of trajectories, that won't be a problem. but with very limited trajectory, because in offline reinforcement learning, there are very few things you are allowed to do regarding this library. So the sample complexity will be very large. Yeah.
Okay.
Thanks for the talk. So I did not understand if actually at the end, did you use reinforcement learning in combination with your with your RNN or not?
Yeah, I use reinforcement learning with this. So the idea is we say the controller have two representations, and we will use this one for learning, all the learning purposes. And yeah, so in the reinforcement learning, really what you put inside as a controller is this RNN. And once you've done that, you can, if you want to do some formal verification, you can try to extract the parameters here and throw it in this, and then you do all the verification that way. And during online deployment, you can either deploy this or deploy that. There will be a slight difference, because for this one, typically we only do the iteration for like 20 times. So although it will be very close to optimal, it's not exact optimal. So there is some problem there. Yeah.
But well, to combine reinforcement learning and your approach with the RNN, did you change the optimization, so the loss function of the reinforcement learning agent, or did you use like PPO or a known algorithm?
Okay. Let me try to probably understand the question a little bit. So basically, in control, usually what we need is some objective function like this. So the tracking error as well as the cost on the control. So but in the reinforcement learning, we need to do a little bit of a tweak. So we have this the original, this so-called quadratic control cost. That is basically the cost that we inherit from MPC. And we need to add some additional terms. For one thing is because usually this cost will be concentrated at the transient period. So you may end up with a controller that have very good transient behavior, but in the end, it's not really tracking the reference very well. So you need to put some extra penalties on the end result. That's one thing, and also here we will turn the constraint violation into a soft objective function. Also, you can do it other way, like for example using safe reinforcement learning and other things. But here we add the constraint violation. And another thing is because we are only doing that RNN for like fixed number of iterations, it will not really convert to the true optimal. But we have some metric on how far it is from the true optimal. So we want to also penalize that. So we don't want the reinforcement learning to cheat. So you really need to learn an optimization problem instead of learning an arbitrary RNN. So these are the additional constraint, additional penalties we add to the cost. So
at the end, what you do is that you encode somehow the objective of the MPC controller into the reward function.
Yes. So this part will be from the MPC. Yeah.
And did you try to incorporate the MPC objective directly into the loss of the RL agent? So not specifically via the rewards, but also in the loss.
Yeah, this will be the
okay,
the
so
loss
exclusively via rewards. Okay.
Yeah, this part will be the loss.
Okay,
yeah.
Thank you.
Other questions? I don't know if online we have questions from the online audience. Okay. So.
Otherwise, I can pose one.
Okay, sure.
in this analogy that you are using the MPC, that is a receding horizon online optimization problem with your reinforcement learning, I was wondering why you're not getting the data offline solving an optimal control problem with the Riccati equation after you penalize and you grasp all the data and after you train your model offline. Why we need to do it online, and how would you change the weighting matrices? For instance, in the MPC formulation, we have prediction and control horizons and weighting matrices. How would you change that, or how that your approach considers those things?
Sorry, let me try to understand. So your question is how to change these matrices, how to get this online? Or?
Actually, well, there are two questions. The first
Yes.
one is why we are using MPC and we are not using offline data, solving many optimization problems offline.
Yes.
Considering all the constraints, why we have to do it in
I
a
see,
receding horizon
I see.
approach, and how would you involve the change? Because at some point you mentioned that your approach considers a longer horizon, so that is a reason why you can foresee constraints in an easier way. So how you can cope with the change of the prediction horizon, control horizon, and weighting matrices within the MPC in your approach? I mean, if we want to...
Okay, I see. Because these slides are created for people within the control background, so probably I didn't make it very clear. But the idea is something like this. So in control, you cannot really solve a very long prediction because the system, inevitably there will be some error or there will be some noise. So you will need to constantly solving this problem online, because you may predict that, okay, I will go like this, but there are errors that I might slightly deviate from my route, and then I need to be able to drive it back. So that's why we cannot just solve an online problem. Another thing is here you also have the reference. So you may, because the reference is probably the human driver give it to you, or some higher order, high level controller give it to you. So if you don't know this reference beforehand. So for two things, one is the reference, the other is there are a lot of uncertainties. So you have to online solving this problem to provide a feedback loop. That's the first thing. You cannot really solve this all offline. The other thing is how do you deal with the predict horizon? So for MPC, the predict horizon actually it's just written here because everything is like that. But really for us, the predict horizon in some sense is in the reinforcement learning how long you run each episode. For example, in this example, for MPC, it's like a three-step look ahead. So it will only look at what happened in the next 3 seconds. But for us, we can create a similar size problem as the MPC. But because we are training this problem in the RL, using RL in a simulated environment, and in the simulated environment, the cost is not what the cost in the next 3 steps. The cost is the cost in the next 300 steps. So that our controller are, in some sense, are a very far look ahead controller. Yeah, so the horizon, we don't really have a horizon. The only thing we have is the size or the complexity, the size of the QP or the complexity of the controller. The horizon is determined in the RL training.
When would you still suggest to use MPC and not your proposed methodology? Because in the results you've shown, MPC is worse, but it cannot be worse in all applications.
I think the thing is, if you really need a very serious kind of verification, because MPC sometimes I would say for us for MPC already it's very difficult to verify. For us, I think more or less it's might be slightly more difficult to verify because for this problem, this is really a non-convex problem. And somehow you have to initial guess what is this invariant set. So there are a lot of some problem like this. It's kind of non-trivial to say that whether this controller, the verifiability is an issue. So if you really need like a very formal verification, if you are in a very, very safety critical system, maybe it's better to use MPC. But I'm not sure how much more difficult this one is to verify. The other thing is MPC is still a little bit more explainable. So here I didn't use explainable, I only use verifiable, because for MPC, basically after you solve this problem, all the U's will have meanings, meaning this is a thing I want to apply at the 0 step, step 1, step 2, step 3. But for us, if you solve this problem, you only get U0. All the other U's are something that you don't really understand what's its meaning. So you only have U0, and if you put in a little bit of predictive model, you can get X1, but that's all you have. You cannot have X2, you cannot have U1, X2, U2, X3. So MPC, we have a little bit explainability, but I would say MPC is still more explainable. Yeah.
Yeah. Yeah, very fast.
So you just mentioned that it's easier to verify. Did you actually try to verify properties within, with the output of your approach or not?
We have tried for this system, but
Okay.
this is not a very large system.
Yeah.
Yeah, and also the proof actually depends on the region. If you just want to prove that in a very small region around the origin, this one is stable, it's very easy. You just go back to a Lyapunov approach. But if you want to prove that in a very, very large region, this one is stable, the proof becomes more and more complex. The
Yeah,
larger region you want
I
to prove
guess it depends on the size of the quadratic program, right? Or
yeah, the size of the optimization problem,
Yes,
and
yeah.
also the region you want to prove this one is stable.
sure.
Yeah.
Yeah.
So we haven't really looked very deep into it because a lot of time for robotics is we just create a demo that will have like 10% success rate.
Okay.
But if you really have like automotive and other applications, you want to look very deep into the verification process of this kind of controller. But for us, we are just creating a demo, so
Okay.
yeah,
Thank you.
doesn't matter that much. Yeah, okay.
Okay, I think that so we will have time to discuss now because we have 10
Yes.
minutes of pause, and also because Yilin we stay
Yeah.
with us for a while. So
Yeah, I will be here until next Friday.
yeah.
Yeah.
So there is time for extra discussion. There are very good purposes. And now we are going to stop for 10 minutes, a short pause. But before, let's thank again Yilin for his presentation.
Okay, so welcome again to the second part of this seminar. So we had a senior fellow giving a first talk, and then the junior fellow will give a talk now. And it's a real pleasure to introduce Yilin Martinez to you. Yilin came to the VUB to do a master in computer science. So she graduated from that master program in 2008. And then the two best students of that year received a scholarship to continue doing a PhD. And that was, so Yilin was one of these students. And then she did a PhD with me. And so therefore, I'm very happy, of course, to introduce her to you. And she will be talking, amongst other things, about what she has been doing in her PhD. And also after, well, returning to Cuba, I must say that Yilin is actually from Cuba. So you did your bachelor there. And we have a lot of collaboration with Cuba, actually with UCLV in particular, because it's a preferred partner of the VUB. And so after going back for a while to Cuba, you joined the lab. And actually it turns out that the work is still very relevant, and you have been collaborating on this idea also with Flanders Make, but maybe you will talk a bit about this. So I'm very happy to see that the ideas are being continued, and I will let you explain. And I will already apologize that at some moment I will need to disappear, go back to the lab, because students still have exams, so I have to be there on time to do some oral exams. But Yilin, yeah, you have the mic. Yeah.
Okay. Thank you, Anne, for the introduction, and well, also thank BrIAS for the opportunity of presenting this work here. As Anne already mentioned, I will briefly give a general idea of the very basic approach that we started with my PhD and how it has been adapted so it could be applied for two different scenarios with Flanders Make. So in general, scheduling problems, I mean, we can say that scheduling is a decision-making process that can be found in many scenarios in our daily life. It can be as easy as you preparing your plan for the day. You have a set of tasks that you have to execute, and in order to do that, you have an objective in mind. So it might be that you have a due date, you have a deadline, or you can also say that you just want to finish all your tasks as soon as possible so you can go home early. So you prepare a plan, having an objective in mind, and typical dispatching rules, as they are called, really common one and really widely used are first in, first out, or shortest processing time. You might want to execute the task you will finish the fastest, or the earliest due date. So maybe you want to give priority to the one that you are supposed to finish by a specific due date. But then once the tasks start to repeat, so if you have to repeat a specific number of tasks during several days, during the week or the month, then we can say that you can start learning from experience. So every time you're repeating tasks, you start thinking, what can I do in a different way? It can be as easy as that, or it can go all the way to different scheduling problems, typical and well-researched scheduling problems that we can find in different scenarios. So for example, you can have timetabling, or we can have the NERSC rostering or the NERSC scheduling problems. We also have project scheduling, so typically you need to define what needs to be done, who is going to do it, and when exactly this needs to be done. And we are going to be focusing a bit more on production scheduling, so I will give a general idea. So for production scheduling, we can say that as a general characteristics, we always need to have jobs that are composed by operations, so tasks that need to be executed in a specific amount of resources for a specific amount of time. So we have basically what we can see here. So we have an operation that needs to have some specific processing time, and for this operation, you might have a start date and a due date. Okay, so it's not mandatory, but you could have also this information. So we typically have different, in the operation research library, we have plenty of benchmarks or problem instances that we can solve from the many different types of scheduling problems we can find. So typically we receive a table, and this kind of table of the different jobs composed by different operations, this needs to be translated as a Gantt chart, which is a typical way to formalize or to visualize how is this the solution for this scheduling problem being constructed. So how we translate this table to this solution is something that we have to do by using a specific method, but we also need to take into account that all the things that you have to the right can also be present. So there could be, for example, setup times. So typical example is not the same to prepare dark chocolate after white chocolate, that's the other way around. So that could be some time in order to prepare the machines for the next task. You could also have order sequencing. So for example here, this job 1 is being composed by 3 operations, and they need to be executed in a particular order. So you can have constraints for the ordering or not. That's also a possibility. You could have operation alternatives. So here we are just saying that you need to execute those 3 operations in order, but you could have alternatives. So this operation can be executed in this machine for this amount of time, or in the other one for this other amount of time. So there's an extra decision over there. You can have machine breakdowns. There could be some delays. And for all these things, we need to be prepared as the best we can. So in the manufacturing scheduling scenario, we can have different types of problems and different objective functions as well. So if we are talking about only one stage, if we have only one machine, then we can say we are talking about a single machine scheduling problem. If, on the other hand, we have parallel machines, then this is the parallel machine scheduling problem. And when this type of scenario gets a bit more complicated and you have multiple stages, then we have to take into account what are we doing here. So if we have jobs to execute, if you only build tables or chairs and you always do it in the same way, so the jobs are always being executed in the same order, then we are talking about the flow chop scheduling problem. If you build, for example, chairs and tables, and each of them has its particular ordering, then we are saying that we are in the presence of a job chop scheduling problem. And if there is no ordering at all, then it's an open chop. These basic definitions can be a bit complicated in the case that we have multiple machines per stage. So if there is an extra decision, so if there can be alternative paths, then we are saying that in the same order for the flow shop, the alternative will be the hybrid flow shop. For the job shop, the alternative will be the flexible job shop. And for the open shop is the flexible open shop. So this terminology, we are going to be explaining it a bit just for the ones in green, so for the job shop and the flexible job shop scenario. Typical objective functions that we can find here when we are working in manufacturing scheduling is to minimize what is called the make span. So that's the completion time for all the tasks. You could also want to minimize the average flow time, so the time the jobs spend in the system, or the average number of jobs in the system. And if we can also work with deadlines or with due dates, then we can also have, or we could also want to minimize the average tardiness, or minimize the maximum tardiness, or the number of tardy jobs that you have in the system. So typical approaches in order to solve scheduling problems can be exact methods. So we can have mixed integer linear programming, constraint programming, branch and bound. But we have to keep in mind that when the complexity of the problems start to increase, if you have a high number of jobs, a high number of machines, then, for example, a simple 10 jobs and 10 machine instance can take from minutes to hours to execute. So this computational time can also increase. And then we also need to take into account uncertainties, changes in general, unexpected events that can occur, not only machine breakdowns, but specific delays and so on. And all this information has to be taken into account at the same time than also solving the problem. And this kind of uncertainty sometimes are a bit more difficult to model in this kind of methods. So that's why when we search in literature, almost all scheduling problems are also being solved by using heuristics or meta-heuristics based on sequencing or dispatching rules. For example, there have been results by using taboo search and colony optimization, genetic algorithms, and so on. And the first application of reinforcement learning in scheduling, we can say, was around the 90s. Then from here, it's possible to see that scheduling problems, they suggest natural formulation as distributed decision-making tasks. And of course, this character of being naturally distributed, it makes the idea that multi-agent systems may be exploited in a purposive way. We were, at that point, starting, let's say, the journey in reinforcement learning. We started collaborating with Anne, and then we said, okay, let's try. We were doing some experiments with different meta-heuristics for these kind of problems, and then we decided to start the journey in applying reinforcement learning for this kind of combinatorial optimization problem, and that's why our objective was to come up with some sort of generic multi-agent reinforcement learning approach for scheduling problems, one that is able to find solutions that are good enough. I mean, we want to have solutions in a reasonable amount of time, that the solutions are near optimal. If they are the optimal, the better, but of course, we are not talking about an exact method. And then, with the same basic approach, we could adapt it in order to satisfy the constraints of the corresponding scheduling problem, so that it could be adapted to different scenarios. And at the end, we also wanted to make solutions more robust by strategically introducing slack times, and I will also mention how this could be done. So briefly, I will be just explaining how we can define this multi-agent reinforcement learning perspective for scheduling problems. We will explain how it could be used for these two scenarios. We will also talk about robustness and criticality, which is an approach that was proposed in my PhD, and we will explain just how to adapt it in order to work with these two scenarios. One we call the kitting case, and also for the light switches scenario. So for reinforcement learning, as the previous speaker was saying, and I won't go into details because most of us already know a lot about it, but we can say that at the end, we want to map situations to actions in order to maximize a numerical reward signal. And at the end, we are going to have agents placed in a specific environment. At each time step, we are going to check what the environment is. We will receive a feedback signal from this environment. And by trial and error and by interacting with this environment, we are going to learn how to solve this scheduling problem. And in our case, we are going to be using the Q-learning algorithm. So at the end, it's a model-free of-policy algorithm that can help us to find the optimal action selection policy. And what needs to be defined then here is by using this algorithm, how we could define what state and action and which is the kind of reward or feedback we are going to give into the agents so they learn how to solve a particular scheduling problem. So at the end, of course, by talking about complex scenarios in the scheduling environment, we will be using multiple agents acting in this same environment. They could have common or individual reward, and I will also talk a bit about that. And of course, we do this because of the advantages of having an adaptive, scalable, and intuitive approach, and of course, due to the ability to solve problems that are too large for a centralized agent to solve. So, in order to apply these ideas for scheduling, when I was doing the PhD, we started checking what has been done and how we can establish something that could be used for the really, let's say, different types of scheduling problems, but can also have better results and through an, let's say, a user-friendly interface can also help the user to communicate with the system and establish which are the preferences that need to be taken into account. And at that time, we found two ways of modeling. In this case, as I mentioned before, I will be talking about the job shop scheduling problem. So we have operations that need to be executed in different resources, and each job has precedence constraints that need to be taken into account. There were two alternatives at that time. So we could interpret it as a single Markov decision process, or we can interpret it as a multi-agent Markov decision process. So we can have like the general, let's say, a centralized point of view by representing the state of the system by the situation of all the resources as well as the processing status of all the jobs, or we can have an agent associated to each of the resources that you have in your system, and this agent will locally decide on elementary actions. Then at the end, we could have a joint action space by being composed by the actions that all the agents can take into account. And at the moment, the authors of this paper were proposing to use, of course, in this case, we are talking about minimizing the time it takes to execute all the tasks. They were using, with the learning algorithm, a cost function that was related or was given by the number of jobs that were in the queue of the system at that specific moment in time. So they were claiming that high costs are incurred when many jobs are waiting for further processing in the system. So we could say that the overall utilization of the resources is poor. So we took this idea. So at the end, we will have as many agents as resources we have in the system. The set of actions is going to give us the state of the agent at that specific moment in time. The action, so for the agent to select an action, it will be to take or to select an operation. So remember, the agents are placing the resources. So at a specific moment in time, I know which are all the operations that are waiting in the queue for in order to be processed by that specific resource. So an action is to select one operation, and then the feedback signals we try with different ones. So we're also using a feedback signal related to the processing time or the solution quality, and we also use one that was a bit more related to the time it will take to process the jobs that are in the queue of the system. Because at some point, there could be two agents, for example, that they both have two elements in the queue, but it's not the same having two with a lower processing time than having two with a specifically higher processing time. And then as objective functions, here for the job shop scheduling problem, we were also mainly working with makespan because we didn't have due dates, but there were other scenarios where due dates were also included, so we were also able to test the algorithm by using tardiness as an objective. So basically, just to give you an example, this is something that this is more or less the idea of how are the instances of the operation research library being composed. So you basically receive a table like this. The first one is the description line stating the number of jobs and the number of resources, and then you have one line per job indicating the operation, where it needs to be executed, and how long it will take. So basically, the last line can be translated in job 5 must be processed first in machine 1 for 3 time steps. Then it has to go to machine 3 for 3 time steps, then to machine 5 for 9 time steps, and so on. So the idea of our algorithm is to take all this information, and then in order to start working, we have precedence constraints. We cannot process operation 1 before operation 0. So we basically have to take the first column, and we find out which are the resources that can immediately start working. So we just launch the first operation of each job. It will go to the queue of the resource that needs to process it, and then for all the resources that can actually execute something now, then all of them will take an action, and then after that, that's how the process is being executed. Once I take an action, then after finishing the processing of that operation, then I can release the next operation of that job, and that's basically what we do here. So assuming that for this agent, we are taking the second operation, and for the second agent, we are taking the first one. We are saying that, for example, in that case, job 3 operation 0 is already executed, so we can release the first operation of job 3, which in this case needs to go to machine 0. And that's how the process is being executed. So every time you are checking which are the resources that can actually perform an action, and then we are just saying, okay, just select one, and then based on that, we were using different feedback signals in different experiments, and I already mentioned them in the previous slide. So as feedback signal, we were using the same that the previous authors were proposing, so the number of jobs that are in the queues of the system, but we also took into account the sum of the processing times of those jobs that are still in the queue, and also we were also giving feedback based on the processing time of the actual operation. We also try with the global reward, so we also want to play with the collective performance, because at the end, if each agent is acting on its own, then at the end, where is the global solution taking advantage from? So we also try with the dual reward, and then we were also giving every agent a feedback signal every time an action was taken, but we also took into account the quality of the solution that was built at the end. We did some experiments, and then we took different groups of instances from the operation research library. There are instances with 10 jobs and 5 resources, 15 and 5, 20 and 5, and many more. And for each of them, we were just doing the experiments and taking into account the mean relative error per group. So here, compared to the previous reinforcement learning algorithm, we can see here that for each group, the algorithm was able to yield better results. And for the other table on the right, we were comparing with the ant colony optimization with the genetic algorithm, and also with the two-stage ant colony optimization. We can see that the algorithm is not outperforming all the others, but is able to find comparable results, and that's what we wanted from the first experiment. So try to find something that is able to find good results, and then by introducing a bit more the idea of having a more robust schedule, that's, say, the strong point of the approach. Besides this, we also did some experiments with the flexible job shop scheduling problem. So here, the idea of the instances is on top, but basically what we need to know here is that instead of knowing in which resource the operations need to be executed, we have alternatives. So here, what we know is that the first operation of job 1, for example, here, can either be executed on machine 1 for 10 time steps or machine 2 for 15 time steps. So for each operation, we have alternatives. Okay, so multiple machines can execute the operations, and the processing time will depend on the resource. That's the main idea in this kind of problem. According to the literature, we have two alternatives here. We can either solve it by using hierarchical or integrated approaches. Basically, the difference is you take into account both things at the same time. So you assign the machine and do the scheduling, or you do the routing first. So for each operation, you decide who is going to execute it, and then you have just a typical scheduling problem like the one I explained before. So here, let's say that we want to go for this kind of approach. So we will do the routing first and then the scheduling. And then we just decided that we will assign for each operation the fastest machine. Okay, what will happen then? So for each of them, I choose the one with the shortest processing time. And the best schedule I can get with that is one that will need 63 time units. Okay? If, on the other hand, instead of choosing the fastest machine here and processing job 1 operation 2 in machine 3 for 18 instead of doing it in machine 2 for 12, then we will see that we are able to come up with a schedule 10 time units. So we will be faster. So we will earn time on our side. So from here we can see that having always the fastest machine, the one that looks like the fastest machine to perform the operations is not always a good idea, because here you can see that machine 3, as it is a slow machine, never gets anything assigned. And then you are keeping machine 2 busy, and it actually needs to wait. So that's also something we wanted to avoid. Then what we did was to also run some experiments. And then in the first phase, we assign an agent per operation. So in order to take care of the routing, we took into account a dispatching rule that is called most work remaining, so MWKR. In this case, the agent will take into account, in order to select who is the machine who will execute me, I will take into account the amount of time that the different operations have already assigned. And then based on that, I will try to choose a machine that is not too busy and that it might finish my processing a bit earlier. And then in the second phase, once I know for all the machines who is going to execute what, then I already have an algorithm that can do that, and that's the one we explained in the first part. Then we ran some experiments. The original work on flexible job shop scheduling problem dates back to 1993, and these are the instances that were proposed. Some of the other algorithms were more recent, of course, and here we can see that except for the genetic algorithm, our algorithm was able to obtain better results compared to the taboo search and also the ant colony optimization and the evolutionary algorithm from the original proposal. So we were able to check that in this case, for the flexible job shop scenario, the algorithm was able to obtain comparable results or good results, and then we decided to check. We also check other scenarios, but it's not time to explain them all. Then we just decided to check, okay, now we are having results that in quality and in computational time, I mean, it doesn't take that long to get them. Let's see how we can deal with robustness, okay? So in real world applications, is something we know is that small uncertainty in the data can make the usual optimal solution completely meaningless from the application, the practical point of view. And then we wanted to check for the robust scheduling, how we can get a schedule that can be, I mean, we can be prepared for something that could happen. And then how can we measure robustness, or how we can incorporate it? So those were the main questions we had at the beginning. And then when searching in literature and in the different publications we found, we saw different ways in which we can do this. So to measure robustness, we can take into account the deviation from the original schedule. So when a user comes to you with a task to perform, you propose a schedule, and then if something happens, you will get something that is not what you propose. So the deviation from the original schedule is what is going to tell you how robust you are. You can also measure it by taking into account the stability or by measuring the number of changes that you require in order to fix the solution once something happens. Then, in order to check how we can incorporate or how we can prepare the schedule so they can be a bit more robust, here there are some approaches that are basically introducing what is called slack times. Here we can say one example could be, for example, the airlines. Once we book a flight, when you book it, you see that it can be, I don't know, for example, a short flight within Europe, 2 hours, 2 hours and a half, 2 hours, 45 minutes. For example, if you book it and it says 2:45, once you fly with the airline, once, twice, you will see that it never takes that time. So the actual flight takes less. But why is the airline then planning a bit more time? Because, of course, you need to take into account that boarding is not taking always the time you should. You should take into account so the traffic, that airline traffic, also in the landing, or if, I don't know, maybe the plane has to arrive from somewhere else before you actually take it. So we can see that even airlines are doing this by introducing slack time. So what is basically the idea behind these techniques is to provide the tasks with extra execution time, that this extra execution time can be used to absorb some level of uncertainty. So you could use, going back to the manufacturing scenario, the knowledge you have about your resources in order to plan when do you think that these resources or the operations being scheduled in this resource will need extra execution time, because this is something that could be a machine that could break down at some point, for example. So you define your breakable resources, and then you protect, let's say, the operations that are scheduled on them. And then, for example, in the example to the left, you protect all the operations, and in the one to the right, you define that only your second resource is breakable, so you only protect the operations in the second one. Why am I making a difference? Because it's not the same to protect everything, because at the end, you are adding extra execution time. So if a user comes to you with tasks or an order, and you say it will take me 3 days for something that someone else will tell you I will need only 1 day, then you might lose a client. So you really have to be careful not to protect a lot, because then you might be saying that you will need more time than expected. So this is a typical solution for one of the instances of the operation research library. So here we have 6 machines and 6 jobs, and here we are showing the optimal solution. So it's showing 55 time units. But here we can see that in order to come up with the approach we propose, we were checking how critical the machines are. So for example, if we, let's say that we are simulating, and we also did some experiments by incorporating some, let's say, unexpected events. So all the bars with yellow and red, these are all perturbations that can happen in the system. We just use specific distributions for that. And here we can see that on a random day, all the machines had a perturbation. So if you keep this idea into account, then you can see that if I use the temporal protection method that I was mentioning before, all the resources can be defined as breakable, and then you will end up protecting the operations in all of them. So our objective, if you protect all the operations here, then you will be telling the user, assuming this is days, that if for the optimal solution you only needed 55 days, let's say, and if you protect everything, you will say that you will need 90 days. So our objective was to take into account in the original solution how critical are the machines. So here we can say that a machine breakdown on machine 2 or machine 6 will not have the same effect than on machine 4. Why is that? Because machine 2 and machine 6, they have too many operations scheduled one after the other, so too many consecutive operations. If something happens in between, for example, machine 6 at the very bottom, between operation 3 and 4, the purple and the green one, it won't have enough time. I mean, there is no idle time in between, so it can't recover from the perturbation or the unexpected event. While on the other hand, for example, machine 4, it does have some idle time in between. So our objective was to define something that is called criticality, and then we allow the user, I mean the user or the expert that is using the tool, to identify the critical resources. So according to the problem you have, you can define when a resource is critical, once we start having too many operations scheduled one after the other. And then we decide the level of protection we want to give. Basically, you can add just a percentage of the processing time. So typically it can be 10, 15%, but of course, this is also that can also be learned by after executing several experiments. If we use this idea, then here we define that the machine is critical if it has 4 operations or more in a consecutive way. And then we were extending the processing time by 10%. And then here, then we will be telling the user we need 69 days instead of 90 as the original method. And that's a bit more realistic compared to the 55, which is the optimal solution. And we did some experiments by using different levels of perturbations, going from 1 to 6, less number of perturbations, and a higher number of perturbations. So we have, let's say, 6 levels of uncertainty by increasing the number of unexpected events. And then we can see in the y-axis here, the deviation in days. So if you use the original method, which is the blue one, then you will start having a higher deviation. Of course, you are protecting a lot. You are saying that it will take you longer than it actually is. But as the number of perturbations increase, of course, you start doing better. You deviate less because you already protected a lot. For the non-protected version, then you start somewhere in between, but you didn't protect, so you will start going up in the deviation as the number of unexpected events increase. And in our case, in the Greek one, we are able to more or less stay stable by taking into account these 2 constraints. So up to here, we were able to have, let's say, a specific approach that can take a scheduling problem plus some user specifications. It obtains near optimal solutions with different levels of robustness. It can identify the critical machines, and using this interface, user-friendly interface, the user can define all these parameters. Sorry. Then we were recently presented with this scenario where a 2-armed robot has to cooperate with a human operator in order to assemble light switches. These light switches can be either black or white. The zone by the people in charge of the control part, the working zone was divided in 4, so that the 2 arms of the robot won't collide. We have 2 workstations, right and left, and there are different constraints in assembly order. There are also constraints for tasks that have to be executed one after the other, so inseparable tasks. And since not all the components are available for the human operator, then of course collaboration is needed. So for this problem, we basically know how the robot will perform, the time it takes for the left arm, for the right arm, and for the human operator to execute each of the tasks. And this is quite similar to the flexible scenario I just explained. So we have 15 actions. They are all mentioned there. And having the set of tasks that we have to execute defined beforehand. For each of the tasks, we have the timing for the different, let's say, resources that we have in line. So the constraints, the ones in assembly order, and the constraints for the tasks that have to be executed one after the other, these are two different sets of constraints that we are receiving, and in order to translate it, this is just being taken into account in the action selection process. So basically, the input file, it changes with respect to the one we had before, and this is also something we had to adapt, but we were able to translate it really, we can say, with some modifications to the flexible job shop scenario. Then the part of assembling the different parts of the light switches can be seen as the operations to execute, the robot arm together with the operator. So we have 3 different resources or machines. They can differ in speed, and they will be our resources. And of course, the use of the zones and the precedence relationship are extra constraints. This is the proposed solution. So we have learning first. We have some sort of routing afterwards. So for each operation, we choose a machine. And in the phase 2, once we decided what will the robot do and what will the human operator do, we just have a sequencing problem in the same way that we have before. And we just executed this. The part of the mode optimization is something that's optional. It was not proposed by us. That's why I'm not explaining it. But if anyone is interested afterwards, it's similar to a local search. This is an optional step. I can explain it afterwards. So we were able to provide a solution. This was the requested format. It is anyway translated through our interface to something like this. And we were having results that we were able to compare to the previous solution they had at the company. They had the mixed integer linear programming first, where for 4 different types of files. So they were building light switches with a single button or 2 buttons. And that's the time in seconds that we'll need to actually execute it. And in this case, our algorithm was able to obtain better results. So for the 15 actions, the 4 zones, and having alternatives between 2 and 4 products with 1 or 2 buttons. That was the first scenario. For the kitting case, there are still things being done here. But the general idea is that full kits need to be delivered to a drop-off location. So if multiple automated guided vehicles are present, they can work in parallel to minimize the total time. So they have to move around by picking the components of the kits and then dropping them off in a specific location. Then they can take only up to 2 kits, and the specific locations in which they can move around, they have capacity constraints. So now we receive input file is an HTML file, so we had to adapt to this. We have components for the different kits, and that's how they are defined. And we have a load time to the AGV and unload time from the AGV. Of course, we have here the locations in the warehouse and the reachability table that is telling me from where I can move to where. So here, once having an input file, we calculate and store the distance matrix. And while there are still kits to deliver, then we assign the kits to the AGVs, following the previous idea. And then we are just moving to the kit storage by loading the times, using the processing time plus the loading time. And then we have to move to the product storage, load everything, and then go to the drop-off location. So there are still things being done here, but it's something we already, we think it's possible to solve it with the same scenario. The results for this so far is that the previous solution was using the PDDL, so the optic solver was able to obtain solutions for 1 AGV and 2 AGVs. We already have solutions for 6. And here, the algorithm is also able to obtain good results. We are also analyzing how to integrate, for the cases where it's needed, the idea of having a deep reinforcement learning for scheduling problems using this DQN approach. So as general remarks, we can say that it was possible to apply reinforcement learning for the different scenarios. The existing approach was modified to other scenarios, I mean, not the basic or the classic ones, but also to extend it to the light switches and the kitting case. The solutions obtained by the modified approach were able to improve the existing ones, and of course, we are evaluating or integrating deep RL for the applications for more complex scenarios. The different papers that were mentioned are listed here. And, sorry for the coffee party.
So, thank you, Yilin, for the presentation. And now it's time for discussion. So, any questions from the audience? Question there?
Hi, thanks for the talk. That brings me back to a previous life in which I was doing research in meta-heuristics. So I have a general question. My intuition is that if you apply reinforcement learning and you get a solution, and you perturb that solution because, for example, in the real case, you have a machine that breaks or there are some other damages, starting from that solution and apply reinforcement learning should be faster and maybe provide better solution with respect to a meta-heuristic. So my question is, what do you think about that? And if you had experiences in trying to approach, to tackle this condition, this scenario? Thank you.
Yeah, thank you. Well, we also have the possibility to start not from scratch, I mean not learning from zero, but if you already have an experience by solving a specific problem, you can start with something that you already learned before. And if something is, I mean, we are also allowing the user to determine whether it wants to learn from scratch or to start from something that has been learned before, but we also allow the user to, to say whether he wants a protected schedule or not. So we can say, I can do this, I don't know, for example, in this scenario, you want to, I don't know, build 200 tables, I can finish this in 5 days. That's the optimal solution, but that's not the realistic one. So we could play something like this, and we can do it in 9 days, for example, if we go for the critical or criticality approach, so we are protecting a bit, or we can have a higher amount of, let's say, protection, and we can say that to be on the safe side, this can take, and you can change the amount of protection you can, let's say, you want to integrate. For the meta-heuristics, I didn't work a lot. I have worked with ant-colony optimization before, a bit with genetic algorithms. I guess something similar, it could be possible, but at the end, for example, if you go for the exact method, some of these constraints are a bit more hard to, let's say, to model or to integrate in the whole scenario. So it doesn't mean that with the other ones you couldn't do it, but from this point of view where we are integrating pretty much all these constraints, and we think it's a bit more like generic approach that is more suitable to make some adaptations better than the other ones.
Other question? Okay.
Thank you very much for the presentation. I was wondering if a machine breaks down, is this algorithm somehow being able to do a rescheduling, taking this information into account? Or
right now, no.
You have to retrain it completely?
Well, in this version, not. But we did some experiments with that. But at the end, the papers we have are with this, that we just introduce some slack time, and then we are letting the machines or use this slack time in order to absorb the perturbation. So we just use the slack time to, like, it's just some part of the time that you had scheduled, and then it will take just this into account. So if the perturbation lasts 3 hours and you had only 1.5 as extra time, then everything will be delayed. But we did some experiments with also that alternative, and of course doing some rescheduling, but it's not the final version that we have, but it's also possible, of course, to reschedule.
I have a second question. In a factory, it's important to know where the bottlenecks are. If I want to buy a new machine, which machine should I buy? Is this algorithm also somehow showing or giving some sensitivity analysis? Where can I optimize?
You could indeed, if this idea of knowing what's the critical resource, I mean, if you have a machine that is really fast, then you will notice that you will use it more. And then by doing that, I mean, following that criteria is how we define the critical resources, but also the kind of operations that the machine can execute. So following this idea, of course, you can identify, and the more critical the machine is, of course, you will use it more. And if this is, of course, the kind of machine you will probably need to buy earlier than compared to the other ones. So the same idea could also be used, I would say.
Any other questions? Oh, okay.
Thank you for your presentation, first of all, and just a question, I'm not an expert of this topic. Also for me, I started working on scheduling problem many, many years ago, but then I moved to other direction. So my impression is that adding a slack time is anyway adding a sort of cost, so the slack time per se is the cost. So I was, my impression that I mean, from the presentation, but as I said, I'm not absolutely expert of the topic, is that the selection of the select time is a bit done, let's say, not by hand, but on the basis of, let's say, reasonable considerations, done by some expert of the process. This is my impression at the moment. There is a way to optimize the choice of the select times, and also, I mean, not only the amount of the select time, but also the distribution over the machines which may require a select time. So there is a way to make this assignment of the select times a bit more, let's say, quantitative and optimized in an automatic way.
Yes, indeed, we could use another learning algorithm in order to learn how to do it. I mean, we didn't do it because it will make it a bit more complex, let's say, but indeed that's also something that could be, let's say, optimized or even learned. So you just play it and you let it run, and of course by using simulations or real data, if you do have it, then you can actually check whether you are integrating the slack times where it's needed, actually. Mm-hmm. And of course, yeah, that's also something we could deal with. At the end, we don't have real data anymore, so we were just, by generating these scenarios with just following some distributions, we were able to check these things. But indeed, it's also something, I mean, for now, we are just proposing something, then the user, of course, if you have experts in of the warehouse, then they will, of course, tell you, these are the machines where you will need it more, or this machine will need more, or even, we don't need it in the morning, the machine gets warm or heated in the afternoon, so just do it in the afternoon. So if you could use expert knowledge, but if not, then what we can do is also apply some learning there, and then, of course, learn this kind of things.
Okay. Yes, thank you very much for the answer.
Other questions? Okay, so if there are no other questions, let's thank again Yilin for this presentation, her presentation. And yeah, so we arrived to the end of the second seminar, and so just slight communication. Next week there won't be the Thursday seminar because we have the first big event of the BrIAS, so the conference on smart agriculture. So the seminars will be postponed of 1 week. So because Thursday and Friday of the next week we will have this conference on smart agriculture. So thanks for coming, and thanks again for the speakers, and see you in 2 weeks.